welcome! What I got for you this time is a problem-solving video on kinematics. So basic one-dimensional motion, and we're going to actually solve a problem. And we're going to use the problem-solving strategy that I had mentioned before. So the problem reads, you toss a ball straight up at 2.5 meters per second from a height of 1.7 meters. Two questions. One, how high does it go? So you toss something up, how high does it go? And second question, how fast is it going when it comes back down to a height of 1.7 meters? So you toss something straight up, how high does it go? And how fast is it going when it comes back to that original height? So there's our problem. Okay, so we're going to use the problem-solving strategy, which means first step, draw a picture. So I have amazingly wonderful artistic skills. So here we go. Here's my very fancy stick figure. And we're going to toss a ball straight up. Okay. And then it's going to go reach a maximum height. Great. That's all you need for a picture. You don't need anything more. Then part of what we have for problem solving is we need to pick a coordinate system. And I'll use our standard coordinate system. Up is positive, right is positive. We also need an origin. And the origin is going to be where we're going to set our initial position, or not our initial position necessarily, where we want our ground level to be. So often with kinematics problems, you just say, oh, the ground is the ground. I'm just going to set 0 to be the ground. So if we do that, that's my origin. The ground level is x equals 0. All right, so let's see. Well, maybe we want to do something different, you know? You could, if you wanted, set your origin to be in a different place. Nope, I'm gonna get this. You could choose, maybe, I want to set here to be x equals 0, because that's where it starts. If you want to do it this way, perfectly legitimate, doesn't matter. We'll come up with the same answer. No matter where you choose your origin, so long as you do the process correctly, you'll come up with the same answer. If it's here, if it's here, if it's here, doesn't matter. One of the reasons I like to pick ground level as my origin is because then I'm mostly working with positive numbers. And I like being positive. So I like having the lowest possible point be my ground level. So I'm not going to do this one. I'm going to do ground level. But feel free at the end of this video to go through and work it through with a different origin. You'll come up with the same answer. All right, so we have, what do we have? A picture, we have a coordinate system, we have our origin, object of interest. What object are we really interested in talking about? Well, we're tossing a ball straight up. I'm going to say the ball is the object of interest. That means we're going to do our knowns and unknowns for the ball. And with kinematics, we have our chart of variables, 6 variables of interest for kinematics. We've got our initial position, final position, initial velocity, final velocity, acceleration, and time. All right, so what do we know and what can we assume? Well, let's just go down in order. Initial position, do we know where it was initially? Well, the problem said it leaves your hand at a height of 1.7 meters. So 1.7 meters from here to here. We start 1.7 meters above, which is positive. Final position, well, that's where it ends up here. That's what we're looking for. That's our target variable. So this is what we're looking for. I'm going to put a question mark there. Initial velocity, and we were given that. We were told that we throw it at an initial velocity of 2.5 meters per second. So 2.5 meters per second, but right now that's only a speed. Don't forget that we have to take into account direction because it's velocity, and we're going up. Positive. V final. Okay, do we know anything about velocity at the end point? I don't think so. All right, so acceleration, and this is in free fall, which means the acceleration is the acceleration due to gravity. And that is our 9.8 meters per second squared. Again, direction, direction, direction. It's downward, so downward is negative. Do we know anything about time? I have no clue how long it takes to go from here to here. All right. That's what we're looking for. Okay, so now we have everything set up. Now we need to plan a solution. So we go to our equations and we say, which equation is going to have the thing I want in it? All right, so we've got the long one has x final. And what else has x final in it? Oh, velocity, v final equals v initial plus at. Nope. Does this thing, v final squared equals v initial squared plus 2a delta x, doesn't have x final in it, at least not obviously. Right here, that delta x, don't forget that delta always means final minus initial. So we have two equations that have the thing we want in it. Our next step is to say, okay, which one is gonna work for us? X final, that's what I'm looking for. X initial, I know. V initial, I know. Don't know time, 1/2 a, I know. Don't know time. Okay, can't do it in one step with that equation. V final, nope. V initial, yep. 2, we know the acceleration. We're looking for this, and we know x initial. Neither one of these equations is going to get us what we need. So are we screwed? Do we just walk away? No. We're missing something. We're missing something. And that's the piece that I kind of glossed over very quickly. You might have said, but wait a minute, when I got to this part right here. Do we know the final velocity? When something is tossed up at its maximum height, how fast is it going? It's slowing as it goes up, stops, and then speeds up as it comes down again. At its maximum height, we actually do know what final velocity is. It is 0. All right, still don't know anything about time. So we do know final velocity, which means this one is actually a known. Ta-da! All right, so I'm not going to worry about that one. That one isn't helpful. This one will get it to me in one step. So I have a working solution. Next step, I have a working solution plan, I should say. Next step is to actually do it. So let's give it a try. And what I like to do first when I'm dealing with an equation is figure out if there are any zeros, because it just makes the math easier and it makes it neater to work out when you're writing. Is anything 0 here? Yes. Velocity final is 0. All right, so right there, I've got 0 equals v initial squared, 2.5 squared, plus 2 times the acceleration, negative 9.8, times delta x. And now here you could put this whole thing in, or you could just solve for delta x. Doesn't matter. This one looks neater to me, I don't know why. And now let's solve for delta x. What we get, if you do the math, is delta x is 0.319 meters. All right, so delta x is 0.319 meters. Are we done? We answer the question? No. The question is, how high does it go? We want to know x final. So delta x is 0.319 meters. That's x final minus x initial. And you could do it mathematically, or you can just say in your head, we started at 1.7 and we went up 0.319. That means where we end up is 2.0 and let's see, well, 2.02 effectively meters. I'm going to round it down to something a little more reasonable. It's going to end up right around 2 meters. X final equals 2 meters. Okay, and now again, don't stop here. Stop and see if your answer is reasonable. If I got an answer of 20 meters, 60 feet, 65 feet, I would know it was not reasonable. If I got an answer that was less than 1.7, I would know it was not reasonable. So always stop and check this answer to see if it makes sense. And then, just make sure that you have a reasonable number of sig figs. Again, I'm not that picky. 2 or 3, both of these would be fine. So I think 2 meters is totally reasonable. So if we start 1.7 meters off the ground, so about here, and we're throwing it at 2.5, is it going to go up to about 2 meters? Oh yeah, that's totally reasonable. Because that's, when I've been throwing stuff, it's been doing about 2 meters. All right, so I think we finished part 1. Yep, we've answered the question. The answer is reasonable. We're good. So now let's go on to part 2. All right, so part 2, the question was, how fast is it going when it comes back down to its original height? So we throw it straight up, leaves at 1.7 meters, and we figured out it goes up to about 2, and then it comes back down. How fast is it going on its way down at 1.7? All right, can we use this? Nope, we can't. We can't just say, okay, well, this was a positive 2.0 meters, and that doesn't help us, because what are we looking for? How fast is it going at the end? Now we're looking for V final. So let's do a second chart. We still start off at 1.7 meters. X final, and V initial, V final, AT. Okay, what's our final position? It goes up, comes to a stop, and then comes back down. And the question specifically says when it returns to 1.7 meters. And that's still positive because the position is above ground. Position is positive. V initial, same thing. We toss it straight up at positive 2.5 meters per second. This is the thing we're looking for. We still have free fall, so we still have the acceleration due to gravity. And we have no idea how much time passes. Okay, so now, same thing, plan out a solution. We need an equation with V final squared. We have, let's see, the long one does not have V final squared, or V final in it, excuse me. We've got the squared equation, V final squared equals V initial squared plus 2A delta X, and we have V final equals V initial plus AT. So those are the two that have what we want. Let's just go through and say, do we have everything? Well, we're looking for this. The initial we have, 2 we know, acceleration we know. Do we know both pieces of delta X, final and initial? Yep. How about this one? V final is what we're looking for. We know V initial, we know A, we don't know T. So that means this is the one we're going to use. Okay, so we have a plan. Let's do the solution. V final squared, which is what we're looking for, equals V initial squared. So that's a positive 2.5 squared plus 2 times negative 9.8 times X final, 1.7 minus X initial, 1.7. Well, isn't this interesting? Take a look at that term. What do you notice? 1.7 minus 1.7? This whole thing goes down to 0. There is no piece here. So what we end up with is V final squared equals 2.5 squared. And so you square root both sides, right? Square root both sides, you get V final equals 2.5 meters per second. All right, does it make sense? Well, does it make sense that if it starts here at 2.5 going up, comes to a rest, comes back down, that is going 2.5 meters per second when we on its way back down? Yeah, there's a nice symmetry. It takes the same amount of time and the same amount of distance to go up to a stop as it does to come back down to that same point. So I think that's reasonable, but it is not yet correct. It is not yet correct. We've labeled this V final. V final is a velocity. Is this thing moving upwards when it's coming back down? I don't even know how to say that. Is it moving upwards when it's on its way down? Nope. This should have a negative sign. It's moving downward. Downward is negative. This should have a negative sign. Well, how did we mess that up? Where is that negative sign coming from? Well, where it's coming from is right here. When you take the square root of something, it has two roots, right? Positive and negative. So many times when we're dealing with square roots in this class, you have to stop and say, oh, which one makes sense? Which one is physically correct? In this case, we know it's going down. You know that physically it is moving downwards. And so we choose the negative of the two roots for that square root. And that's where that negative sign comes in. All right, so the number makes sense that it's symmetric, going up and going down for the same height. Its direction makes sense. It's, I hope that's a reasonable speed. We were told 2.5, so I'm hoping that's a reasonable speed. And I think we've answered the question. I think we've got it. So there's a part 2 example of problem solving with one-dimensional kinematics. I hope this makes sense and that you see the value of doing the problem solving process, especially that last piece. Check your answer. All right, good job.